Hello everyone. Today we're going to be talking about disk and washer method and how areas on the curve can determine the volumes of shapes. Now, so before we get started on disk and washer method, I would like to introduce differentials and how to interpret an integral as a brief recap. All right. So right here I have a graph, and let's say this is the graph of x cubed, and we're going to be taking an integral, right? We already established in prior that, and let's say this is a point A and this is point B, and those will be our limits. Nonetheless, let's get into it. We already established that the area under this curve is an integral, right? So we're trying to find the area under the curve, coincidentally enough. So we're going to set up an integral from our limits B and A, and we'll have our graph. Our graph is x cubed and dx. We already know this is this is the integrand right here. That's what we're integrating basically. But what does this little dx stand for? And we haven't really talked much about this, but dx is a differential of x. And how this works is basically in an integral, we are multiplying these two things together. And how does this help us find area? Well, dx basically just means that we're going to take an infinitesimally small piece of this graph, right? An infinitely small piece, right? And that will be our dx, right? It's a very, very tiny piece, an infinitely small piece, infinitesimally small. And we're going to multiply that with the curve, right? Or at the instance of the curve. Because if we have a dx right here, right, and our x is like 2, right, we have an infinitely small width at a certain length. And what's length times width? Length times width is just the area of a rectangle. So what we're doing with an integral is we're taking infinitely small little, for better reference, I'm just going to do a bunch of lines here and going to treat all these lines as dx's, right? All these little lines are dx. And because we're taking infinitely small pieces and multiplying it by the the curve, we can get an extremely precise measurement. But with an integral, you take you take a completely accurate representation, and that's because it's the antiderivative. But that's another topic for another video. So basically, to find the areas, we're basically doing these infinitely small rectangles under the curve. And that's all dx is, an infinitely small piece of width. Now, this will be relevant here in a second when I introduce disk method. All right. So uh this is a disk method on one of our old prior quizzes. So let's draw another graph right here. Perfect. And the curve I'm going to be drawing is that of uh, y equals ln x. And then we have a few restrictions. Now, this is getting into disk method. And y equals 0. Y equals 0 is just the x-axis. And we're going to rotate it around x-axis. That's our axis of revolution. All right. And then E of 3 is at some point later. It's just a number. And we're given this little area right here. Now, because it's ln x, it crosses the point at 1. Bingo. this is our graph. This is our area. Now, if we rotate it around the x-axis, very difficult to imagine, we're almost given a bowl, almost, of some sort. We're given a bowl, but it's more like a semisphere that we have. So, and let's draw our axes here so you can better kind of envision this. So this is our y-axis, and this is our x-axis that goes directly through it. And now we're trying to find the area of all of this. Well, it may seem taunting at first, but it really isn't that taunting, especially with disk method. So, your first approach would be, well, if I were to give this to you and you do nothing about revolution, you would probably be scared. But just like before, how an integral takes a little point, takes an infinitesimally small piece and multiplies and adds all of that until from one point to one point, and that will give us the area. Well, we can do the same, but instead of doing it with lines now, if we take an infinitesimally small piece, right, of this graph, right, it's good from a side profile, it's going to look like a line, right? But if we turn it over, we see that it takes on a whole nother shape. It takes the shape of a circle. Now, I'll ask you this. Do we know the area of a circle? And yeah, the area of a circle is just pi r squared. Correct? So how would we get the area of all of this? Well, we can integrate a bunch of little disks, because we're going to treat these circles as disks almost, because a disk has it has some width, right, on the side here, but because it's so small, it's going to be dx for first and foremost. But we're going to be summing a bunch of disks, because that's all that an integral does. It sums a bunch of things, and we're going to be summing a bunch of different circles. Now, one thing you'll notice is that if I were to take a dx over here, right, an infinitesimally small piece again, our circle is different. It's smaller than that one. Why? Because the radius is smaller. How? Now, if you look into this equation, for one, pi is a constant. We know that pi is a constant, but radius is not. Radius changes throughout the different instances that we go on. So we're going to create an integral right here. So how would you find the area of that shape? Well, we're going to take an integral from these two places, right? Because in reality, we're just trying to find the area of this, right? And to find the area of this, these two are limits, correct? But because we're rotating around now, we're going to be using the formula for a circle or a disk, right? So we're going to have pi r squared dx. Now you see that we have two conflicting variables. We have a r and we have x. So we have to either get x in terms of r or r in terms of x. And the easier method is to get r in terms of x. I don't want to do anything. Well, first let's take out the pi, because pi is a constant, and that can be done on all. And then we're left with r squared dx. Now, we established that that's a radius, right? So if we compare, when we take that dx, right, we're going to say that, let me grab another color real quick, that this is the radius, right? Yeah, because all down here, that's the diameter of a circle, and that piece up here is going to be our radius. So how do we get the radius, you might be asking? Well, we take the curve, right? We just want from the curve down. We want that length. And to find that length, we just use the curve minus the axis of revolution. And the axis of revolution in this case is 0, so it's just ln x. So we plug in ln x for r squared, because ln x is our radius. And when we rewrite this integral over here, don't forget your pi, we're left with pi e to the 3 1 ln x squared dx. And that's all there is to it. And this is from one of the quizzes. If this is the first quiz, if you want to go check it out. And that should equal 309,220. And that's just disk method, right? We have a disk. We sum a bunch of these disks, right, using the integral, right? And that helps us find the area. Pretty simple stuff. Now, moving on to washer method. Washer is a little more complicated. Okay, we'll have a new graph here. For washer, this is on the first quiz again. This is the very first problem on the quiz. But let's say we have the curve y equals root of x, which looks a little something like this, right? And what we're bounded by y equals 2, x equals 0, and that's it. All right, and the first part of this question asks us to find if the axis of revolution is the x-axis. So we're going to be revolving it around the x-axis. Now, this is a washer problem, and I'll explain a little further. Right? Let's say that's y equals 2 right there. So the area under this is just this over here. Now, as you can see, we have a little problem. We have from here to here, we have all this empty space. Correct? We're going to count that as empty space. Now, when we rotate it around the x-axis, the shape we get is almost like a bowl, almost. Let's see if I can accurately draw this. Right? And I'm going to use pink here to demonstrate that area that's gone. All this area is gone, but this, and this is inside the shape, but around it, there's a hole. Now, when we split this shape up, right, if we take a little size of the piece, we see that we don't get a disc anymore. What we get now is a circle, but more importantly, we get almost a washer. And this is all our blue area, right? This is the area we're actually trying to find. And it's almost like a donut, and this is where the hole is located, right? And at any point, it's going to change up a bit. If I were to take a differential little small piece here, the hole is bigger and there's less blue area. But over here, there's more blue area and vice versa. Stick with me. Now, we already know the how to do disk method. And washer method, I should probably go back up here. What washer method does is, so we can determine the radius from here to here, right? That radius right there is just from the curve all the way up to here. But there's going to be a hole at some point. But thankfully, we can also determine the radius, or this length right here, from the curve all the way to the axis of revolution. And that will be our other radius. So we'll have one radius and we'll have the other radius. Right? It's like we're having two disks and one, and we have to subtract them because we don't want this area right there. And we're gonna, because we can determine the radius of this one, we can determine the area of this one, and then we can determine the area from all of this, and we can just subtract this area and this area. And bingo, we have the area of our shape. So, to do this, we'll take, so let's write out the integral first. So first we have to determine where this intersection occurs, and we can just do this by setting both of the y's that were given equals to each other. So y equals 2 and y equals root of x. So that's going to be root of x is equal to 2, and square both sides, and we get x is equal to 4. And that's where they intersect, at 4. So we have one of our limits, and the other limit is 0, because we have x equals 0, and x equals 0 is the y-axis. So now that we have our limits, don't forget about pi. Pi is right there. Now, for washer method, we have to first determine the area of the big circle. And to do this, we have to take the top of the curve all the way to the axis of revolution, and it will give us the entire area here, right? And that radius right there, that yellow line, which is we're going to treat as our radius, that distance from there to there is 2 minus 0. And the 0 goes away because, so we just have 2 squared. And then we're going to subtract that by the other radius. Now, to determine this radius, it's from this curve all the way here, which is just root of x, and then our axis of revolution is 0. And that goes away too. So we just have 2 squared, and don't forget dx, minus the root of x squared. And that's what our integrand is. Now, if we simplify a little bit, we have 4. So we have the integral from 4 to 0, pi on the outside, minus, and then those two go away, minus x dx. All right, this is a very simple thing to integrate. We have 4x minus 1/2 x squared, and our limits are 4 to 0. When we plug in 4 and 0, we get 16 minus 8, because that's 16 and divide. And then when we plug in 0, we get minus 0 plus 0. Those go away. They're just zeros. And whenever you get, and don't forget about the pi. It's a very common mistake. When we subtract that, we just have 8 multiplied by pi, 8 pi. And that's just the answer to it. But back up here, all that washer is that we're making 2 disks and we're subtracting them from one another. And that's why we have that subtraction problem there. This was just a very basic washer method. And I know it might be a little confusing still, but I hope to clear things up in the next cross sections and washer method video. All right, peace out.